So in this video, we're going to discuss solving a system of differential equations in which the characteristic equation has complex roots. Often when we consider diagonalization, we summarize with this theorem that if the coefficient matrix A of a system y prime equals ay is diagonalizable, then the general solution of the system can be expressed as taking function multiples, if you will, of eigenvectors. And we summarize by saying that eigenvectors make wonderful basis vectors to get the solution space. So we want to take that approach with regard to a system of differential equations where the coefficient matrix will actually have complex eigenvalues. So if we want to construct a general solution of x prime equals ax involving complex eigenfunctions, and then obtain a particular real solution that fits the given initial condition, the question becomes, well, how do we extract real solutions from complex conjugate roots from the characteristic equation? And oftentimes textbooks just tell you to look at certain aspects or certain parts of the eigenfunctions and just extract that information, the real part, the imaginary part. But why does that work and what are they talking about? That's going to be the subject of this video. So looking at x prime equals ax, right, where x prime means you have functions x1 of t, x2 of t, and you're taking their derivatives, equaling a coefficient matrix of -3, 2, -1, -1, times those functions x1 of t, x2 of t. We want to figure out what x1 and x2 actually are. They're going to be functions of t. And I'm giving you here this initial condition that when you substitute t as 0, into each of those functions x1 and x2, you get 0 for x1 and 3 for x2. So this will come into play later as we solve for particular constants. All right, so let's get started with getting the characteristic equation. We go about our usual business. The characteristic equation of A is simply find the determinant of lambda I minus A equals 0, which would look like this. But in particular now, when you do this, you have an interesting quadratic expression, right? We take the determinant of this 2 by 2, and we organize our lambdas, and lo and behold, we get lambda squared plus 4 lambda plus 5 equals 0. Looking for two integers that multiply to give you 5 and add to give you 4, not going to find them. Quadratic formula comes into play here. We have complex roots. In fact, going through the quadratic formula, we get two complex conjugate roots, namely lambda 1 equals -2 plus I and lambda 2 equals -2 minus I. So again, lambda 1 equals -2 plus I and lambda 2 equals -2 minus I. Two distinct complex conjugate roots to this characteristic equation. So the complex eigenvalues of a real matrix will always occur in conjugate pairs. We know that because it came from the quadratic formula. We have plus or minus. So we have conjugate pairs all the time whenever you have complex eigenvalues. And as it turns out, their corresponding eigenvectors will also occur in conjugate pairs. We could prove that initially and then show how it actually turns out to be the case in this problem. So we know what eigenvectors are all about, right? Ax vector equals lambda x. That means we have an eigenvector x associated with this eigenvalue lambda. But if we take the complement of both sides, so you have ax bar equals lambda x bar, that means that a bar x bar equals lambda bar x bar. But wait a second. Matrix A was made up of real entries, and the complement of a real number is just itself. So since the complex conjugate of a real number is itself, we really have matrix A again, right? A bar is matrix A times x bar, the conjugate of the vector x, equals lambda bar times x bar. Well, lo and behold, for matrix A, we also therefore have an eigenvector x bar associated with the eigenvalue lambda bar. So again, this shows that the eigenvalues and their corresponding eigenvectors occur in conjugate pairs. So that's what we're going to expect to see as we proceed. So let's actually do that. Here's the structure, once again, of the characteristic equation applied to a linear system, a linear homogeneous system. And now as we substitute our eigenvalues, well, what's going to happen? Well, let's take the first one. lambda 1 equals negative 2 plus I. That's our first eigenvalue. If we substitute that in our structure here, we will get this matrix. You'll notice that it still has some complex numbers on the main diagonal. So how are we going to solve for x1, x2 in this particular case in order to get the eigenvector family? Well, you might be thinking of row operations and then you're saying, oh, we got to deal with complex numbers in that process. Well, you could do it that way. But also think for a moment, what do we expect here? We had two distinct, albeit complex, eigenvalues. So we expect that each one of them is going to generate a linearly independent family of eigenvectors. So we know we're going to get a non-trivial answer in this system. So since we have two distinct eigenvalues and we know that the resulting systems will have non-trivial solutions, that tells us something about the reduced row echelon form of this coefficient matrix in this system even before we go through those motions of finding it. We know that if we did find the reduced row echelon form, it must have a row of zeros. Reason? Well, if it didn't have a row of zeros, then the RF would be the identity matrix, which means that the only solution to this homogeneous system would be the trivial solution, 0, 0. And you know that a zero vector, 0, 0, cannot be an eigenvector, nor are we expecting to get 0, 0 in this case, because we have two distinct eigenvalues, going back to our eigenvalue theorems. So we know we have a row of zeros, implying that each row really in this coefficient matrix must be a scalar multiple of the other. So really both equations in this system that you see determine the same relationship between x1 and x2. You could say they're like repeating themselves, which means either equation can be used to express one variable in terms of the other. Now if I had my choice to use one of these two equations to express one variable in terms of the other, I know which one I'm going to pick, right? I'm thinking this column represents what's going on with x1, right? This is the x1 column, and this is the x2 column, and if I want to solve for one variable in terms of the other, I'm looking at the second equation. I'm looking at down here because I already have a coefficient of 1. So clearly from that second equation we can easily conclude that x1, right, you just move this coefficient, albeit a complex coefficient, you move this coefficient over to the other side, it becomes the negative of itself, so it'll be 1 minus I, and you let x2 be the free variable, so this will be the position for x2. So if we let x2 equal, say, the parameter s, then x1 would have to equal 1 minus I times s. Or you could just say the eigenvector family is s times 1 minus I times 1. So we have captured the first eigenvector family for this particular system. Now, what will happen as we use the second eigenvalue, which is the conjugate of negative 2 plus I? Will we also get the conjugate of this eigenvector family? Now we know the conjugate of 1 is 1, so that's going to stay the same, but will we get 1 plus I in the first position for the second eigenvector family, as we suspected from this proof up here? Well, let's see. So here's our structure again for that homogeneous system. Now we're going to put in our second eigenvalue. And as we do that, again, we have a homogeneous system that has some complex numbers in it, taking the determinant. Looking through that, once again, we can say, well, in order to avoid all that maneuvering with regard to row operations or determinants and checking through that, we can instead say, hey, look, these really say the same thing. Let's solve for x1 in terms of x2. And lo and behold, looking at the second equation again, it has a coefficient of 1. If you bring that over to the other side, you get 1 plus I times x2 is what x1 equals. So setting up a parameter, we have x2, the free variable, could be t, and x1 is t times 1 plus I. Notice the eigenvector family is involving the complex conjugate of the previous eigenvector family as we anticipated. So complex conjugates once again appear. Well, now that we got the eigenvector family, we're going to create these eigenfunctions with their corresponding expressions involving e that you saw before. We're now going to apply that theorem that we mentioned initially. Okay? So let's summarize what we have so far. We were given this system, right? We were given this system of differential equations with this coefficient matrix. Here's the initial condition. We found two distinct complex conjugate eigenvalues. We now wish to create the solution by building on that theorem we talked about at the outset. We're going to take e to the eigenvalue, first eigenvalue t, times the first eigenvector family, plus constant multiple of e to the second eigenvalue t times the second eigenvector family. Well, what does that look like in this case? Well, here are the eigenvalues. Negative 2 plus I was lambda 1, and negative 2 minus I was lambda 2. So here we have an expression for the general solution to this system of differential equations. This is correct. However, there are a lot of complex numbers involved in this. And although complex eigenfunctions, as we call them, are convenient, especially as electrical engineers will tell you for their evaluations, real functions are what most people are interested in. They're more appropriate for many other purposes outside the realm of electrical engineering. So we want to see how can we extract real solutions to this system of differential equations from this complex expression. Well, we go back to a very familiar formula called Euler's formula. I'm going to alter a little bit. If lambda equals a plus bi, then what would e to the lambda t really mean? Well, we could break that up, right? Distribute the t and then use the properties of exponents, be e to the at times e to the ibt. And using the generalized form of Euler's formula, e to the I mu t would be cosine mu t plus I sine mu t. We can certainly rewrite this expression, e to the at times e to the ibt, as e to the at times cosine bt plus I sine bt. So if you forgot about Euler's formula, remember the general development of that is to take the infinite series for e to the x and substitute I theta into there, and then you could build that using powers of I. That's best handled in a Calculus 2 course, but most people just remember the formula, Euler's formula. Now we're going to use it to our advantage. Okay? So for our system, what would happen if we replace this? What would happen if we replace this structure for the e to the negative 2 plus I and e to the negative 2 minus I expressions of t? Let's look carefully. We know we have e to the at, so a is the negative 2, corresponding to a plus bi. And what would b be here? Looks like we just have a 1 there. So we're going to have cosine t plus I sine t for the expression e to the it. Okay? We keep this column vector involving a complex number. We keep that. Let's look at the second one. Again, a is negative 2, so we have e to the negative 2t appearing. But it looks like we have a negative 1 it. So b is negative 1, so we'd have cosine negative t plus I sine negative t. Now we know something about cosine and sine. Cosine is an odd function. Excuse me. Cosine is an even function, and sine is an odd function. So the cosine of negative t would just be cosine t. And the sine of negative t would put a negative here instead of a positive. So we could rewrite this as such down here. Okay? So again, this slide shows how we use Euler's formula to just rewrite what we had before. And we're going to see why we're going to actually do this, because again, our goal is to extract a real valued solution. So again, starting with this altered form, still got a lot of i's, a lot of complex numbers going on here, but starting with this altered form, we're now going to actually distribute and see how we can extract a real solution. So let's actually multiply cosine t plus I sine t by both components here, and cosine t minus I sine t times both of these components. What would it look like? Well, if you take a moment, you could easily see, right, distribute it out, FOIL it out, you would get cosine t minus I cosine t plus I sine t plus sine t for the first entry, and cosine t plus I sine t for the second. Notice we still have our c1 e to the negative 2t hanging out on the outside, and doing similarly over here with the second vector, we get this expression. Now we want to extract the real part and any part that has I with it. Okay? So maybe you can think here for a second, anticipate what the slide is going to show next, right? Looks like we have some I stuff going on here, right, as well as here. So maybe if we just highlight the I components, we could easily see the separation of the real and the imaginary. So on the right side, we have some I stuff going on here, as well as here. So what would happen if I extracted those I pieces out and set apart the real components? It would look like this. Let's look carefully. So everyone see the I stuff? I take the I on the outside, and I have, let's see, sine minus cosine it looks, and just sine, there it is. Those are the I pieces. Notice the I is on the outside. And of course, everything I didn't circle is simply real to start with, so I'm going to put it to the side. Notice both have the constant and the e to the negative 2t as multipliers still. We'll call that C1 times, we'll call that x1 solution. And on the right side, all the stuff with I, if I take out the I, I'm left with cosine minus sine and negative sine. Notice the I is on the outside. And the real stuff that I didn't circle all comes together. Here we'll call that C2 times x2 vector. Right? So looking at this, can we tell what the real and what the real solution would be? Right? If we think about this for a moment, there are two ways to see it or to appreciate where the real solution comes from. We're given x1 and x2. They're definitely solutions to this system combined together here in linear combination. Kind of reminds us of the superposition principle. By the superposition principle, we know that if we have two solutions, namely x1 and x2, then the sum of those solutions should also be a solution, and the difference of those solutions should also be a solution to our system. So let's try that and see what we would actually have result from those additions and subtractions of x1 and x2. So I tried to do both at the same time here. Here's x1, here's x2, less the constants in front. We'll just focus on the functions, the eigenfunctions themselves, some real, some complex. Right? And if we add the two, let's do plus first. If we add the two, we only seem to be getting 2 times the first column vector of real functions involving no I at all. Do you notice why that happens? Do you see how the elements, the components in the second set of vectors, they're additive inverses of one another? So they're going to give you the 0 vector. They're gone when you add them. So you're only left with 2 of these. And there it is. But if you subtract, let's do the subtraction next. If you subtract the 2, now these 2 are gone. And by subtracting, I have 2 of these, which I could take out the 2 in the front. Remember, the I was still hanging on the outside. So if you look at this, we have a coefficient of 2 times this eigenfunction and a coefficient of 2i times this eigenfunction. So the constant multipliers, you could look in the complex universe, you could look at 2 and 2i as just constant multipliers in front of these real valued function solutions, which really correspond to the real and imaginary parts, as most textbooks call them, of x1 or x2. That is, what's the real part in the front, what's next to the I part in the second part of a complex number. They call those the real and imaginary parts. And that's what they're trying to express in those textbooks. They're saying, hey, look, these expressions really correspond to those real and imaginary parts. So why don't we just use them? In fact, if we look back, which is often a good thing to do in mathematics, if we look back at the expression we had before, could we have discerned these 2 real components as the real solutions to our system right from the outset? Let's see. This is what we had before. You'll notice these 2 match perfectly, right? The first part, cosine t plus sine t, cosine t, same thing here. The second parts don't look exactly the same. However, look carefully. Right? Look carefully at these vectors here, this one and this one. Let me see, I could circle that, have you think about that for a moment. Look carefully at this, all this stuff in here, and all this stuff in here. They're not the same, but can you make them the same? If you were thinking factoring out a -1 from the second column vector, and it'll look exactly like this one, you're correct. And if we do that, we factor out a -1, I'm going to just call that negative C2 that would result by factoring out a -1. I'll call it constant 3. So really, when we look at these two solutions, right, when we look at constant times x1 vector, which was this piece, and then constant times, right, x2 vector, which was this piece, right, you can see that they really involve both pieces, x1 and x2, really involve the same real eigenfunctions. They really involve the same real eigenfunctions. So that's why textbooks often say, look, by factoring out that -1 and the imaginary component of x2, you could clearly see that x1 and x2 are really conjugates of one another at first, and then they involve the same real eigenfunctions for both their real and imaginary parts. So most textbooks then go on to say in a footnote somewhere, one can use x1 or x2, but not both, to produce two real linearly independent solutions. So what we're saying is, whichever one you use, you're going to get the same real functions involved in the solutions, and that's why we usually just focus on one of the eigenvectors to create those two real pieces, those two linearly independent pieces. Which leads us to our last part of this discussion. How can we show that they're linearly independent? Right? A lot of times textbooks will say, well, it can be shown. Well, how do you show it? How can we establish that these eigenfunctions, right, which are e to the -2t times this column vector and e to the -2t times this column vector, right, how can we show that they are linearly independent? Well, this takes us back to another concept you learned in linear algebra called the Wronskian. Okay? Now, look at these functions. Whichever eigenvector you use, the column vectors that are involved have two rows of functions. We have a 2-by-1 matrix structure for each of the eigenfunctions. So we can establish linear independence by using these column vectors in a Wronskian structure. Remember, a Wronskian is just a linear system that you set up to determine, well, what coefficients can be used to multiply the functions involved to get 0. If the only answer to that question is 0, then you have linearly independent functions. So if the Wronskian, remember, if the Wronskian of a set of functions is not equal to 0 all the time, remember the Wronskian is a determinant. The determinant's not equal to 0. That means that matrix, the coefficient matrix that's involved in the system is invertible. And if you have an invertible matrix, coefficient matrix in a homogeneous system, then the only solution is the trivial solution. And if that's the case, then you have established that those functions are linearly independent. So that's a little recap of how to use the Wronskian. What does the Wronskian look like in this case? Well, if you go through the determinant 2-by-2 structure, you'll actually have an e to the -4t involved in the process, which you could take on the outside. So you're really focusing on just finding the determinant of these functions. And if you do that with a little Pythagorean identities helping us out, we get a result of e to the -4t. That's an exponential function, which is never equal to 0. So since the Wronskian of these two column vectors, x1, x2, of eigenfunctions does not equal 0 for all values of t, then that means that the column vectors used to form x1, x2 are linearly independent. Thus, the real solution to the system is finally in our grasp. We were given this system of differential equations. We're given this initial condition. So we can express that solution simply as C1 e to the -2t times this column vector plus C2 e to the -2t plus this column vector. And now all that remains for us to do is find out the values of C1 and C2. We know we have linearly independent pieces. We're not repeating ourselves. We can now actually figure out what C1 and C2 are. So with this given initial condition, remember what that means. Wherever you see t, you put 0. And wherever you see x1 and x2, you put 0 and you put 3 respectively. So what happens, right? We're going to put 0 and 3 here, and everywhere we see a t, we're going to put 0. And you would get this. Let's see if we agree with that. Let's just make sure of that. Okay. So you know when you have t is 0, you have e to the 0. So these exponential functions, they're just going to turn into 1s. I'll just put 1 there. Okay. And cosine of 0 is also a 1. Sine of 0, that's going to give us a 0. Cosine of 0 is 1. So looks like I have 1, 1. That's what I have here. That's correct. And sine of 0 is 0. Cosine of 0 is 1, but you have a negative in front, so we get a negative 1. And sine of 0 is 0. So it looks like I have it correct here as well. Negative 1, 0. Just want to walk you through that really quickly. So now we want to find out what C1 and C2 actually are. You put in a linear system, and you can actually see just putting them together that C1 equals 3. And then you could tell from this first row that C2 must equal C1, so C2 is also 3. So that leads us to the nice, neat answer. Finally, we've reached our goal, a real solution to this system of differential equations that had complex eigenvalues. We simply substitute 3 for C1 and 3 for C2. So I hope this gives you a clearer picture of why textbooks say, hey, you take the real part, you take the imaginary part with regard to the eigenvectors, right, and you make the real solution to this system. Why is that the case? And why do you only have to focus on one eigenvector family? Well, all those things came together in this video, showing you that they really are saying the same thing and lead you to the one unique answer to this problem, which is really an initial value problem in a system. Okay? So we hope you enjoyed that video, and we hope to see you next time.